All right, class, welcome back to another installment of Natural Intelligence, the blueprint for AI. Now, of course, remember, we are building our base, our foundational meta learning skill, the skill of learning how to learn before we dive into actually learning some of the AI principles and fundamentals. In tonight's class, we will be discussing lesson number 3, which is the bottleneck. Right, we'll be managing the working memory limit, and just a little peek into that particular axiom. Your brain can only hold 4 chunks of information at once, right? And similarly for our AIs. Now, let's talk a little bit about the recap for the last session. Now, last session, we went in and we jailbreaked the Gatekeeper, or the RAS, which again is the brain's attention filter. And we discovered that it processes, or at least it's encountered with at least 11 million bits of input, but only 50 bits actually get through in your brain, right? So that's a massive loss of data that's not coming into your brain. And so we learned last class how to jailbreak that. If you did not watch that video, please go back and brush up on that, because it does tie into what we're talking about today as far as the working memory. And then we also learned last class that the RAS, or the reticular activating system, it does prioritize primarily 3 things: survival, novelty, and self-reliance. So if it's not one of those 3 things, your RAS works against you to retain that information. We also learned that most learning fails because it never passes this gate, this RAS, reticular activating system. And we learned some ways to hack it. We learned that if we prime the RAS by framing input as personally relevant, and we learned that maybe you could write and jot down some things using your physical writing ability before you go to bed, to really set the intentionality before you go to sleep, to let your subconscious mind work on things. We learned that if you tie in your emotions to a particular subject or material you're trying to learn or ingest, that helps tremendously, amongst some other things as well. And then finally, for our build objective, we had our architects in our builders build an input script and a system prompt, respectively. And they were able to go into the requirements for each one of those, just to put that information into practice. Now, key insight from last class is that the information that passes the RAS now faces a second constraint, the working memory, and that ties us into what we're going to be talking about tonight. So the working memory can be broken down into, again, the biological hardware of the working memory, and we're going to relate it to RAM, okay, or random access memory, for all of my tech geeks out there. Now, the mission today is to manage that 4 chunk working memory limit, the narrowest pipe in your cognitive system. So again, the very minimal amount of information is going through that pipeline. We need to figure out some ways to either compress the data or maybe utilize that full pipeline as much as possible to get as much information in to our working memory, because again, we want to be able to retrieve and recall that information, because that's when the learning actually takes place. Now, the mechanism itself is the working memory. It's the brain's RAM, the RAM, or the random access memory. Now, it's a temporary workspace that holds and manipulates information in real time. So something to think about this as is that you can think of it almost like short-term memory or cache, where it's not information that, like, for example, your childhood memories. We're not talking about that. That's not working memory. That's more long-term memory. We're talking about memory in relationship to if you read a book, if you listen to a podcast, if you watch a tutorial or participate in a tutorial, that information could potentially go into your working memory so that you can then use it on the fly and at call. So that's the mechanism in particular we're working with. Now, obviously, the problem with that mechanism is that we really cannot exceed 4 chunks of information without that being overwritten or essentially just cast out. So every lecture, every tutorial, and document dump is fighting against that limit. Now, the science behind it, Miller in 1956, he approximated that there was 7 plus or minus 2 chunks of information that the brain could handle. That science was actually updated by Cowan in 2001, and the latest real-time limit supported by science is 4 chunks, right? So you can check those 2 researchers out if you want to see the scientific evidence of this particular topic. All right, gang. So what is working memory actually? How does it work? Well, first thing we got to talk about is the capacity. It's 4 chunks of information. So just think of it as if you're ingesting, let's say you're watching a lecture or you're watching a tutorial, right? 4 chunks at a time. So maybe 4 particular topics or 4 subdomains or 4 subject matters that you're actually able to retain or ingest at one time. So you have to be mindful of this, right? Maybe if you're reading a book and that book is going over a few different concepts, try to keep the number of concepts to 3 or 4 concepts within that material before you continue reading, so that you can, again, get that information into your working memory and repeat it so that it holds it and gets steadfast. Now, the duration, 15 to 30 seconds without rehearsal. So again, if you don't, let's say you're reading a chapter, you're listening to a podcast, once you hear that or see that information, you have about 15 to 30 seconds without any rehearsal, without repeating it, without seeing it a second time, for that information to sit in your brain. Now, obviously, there are some people that varies a little bit just depending on their own cognition, but in general, these are the averages. And the function is going to be to hold and manipulate the data. Again, this is like our staging area inside of our brains where we're just putting information almost temporarily because we anticipate using it very quickly, right? Again, it's working memory because we're working with it. And then failure mode, overwrite or decay. So again, if that information does not uh, fit into our pipeline, if it exceeds that 4 chunks that we were talking about, right? That information, or if we don't use it, that's another thing you can think about. If we don't use the data or the information right away, it will be overwritten and it will decay. It will just essentially atrophy and we won't get it. It's that whole use it or lose it axiom there. Now, the location is in the prefrontal cortex and the parietal region, excuse me. So it's a little bit different than the RAS, which was in the base of the brainstem. Now we're moving to the front of the brain for this particular mechanism. Now, the workbench analogy, if we're looking at things as a kind of related to something physical in the world, something more tangible, think about it as your desk, okay? Your desk can only have 4 open documents or maybe 4 objects on a desk at a time. You add a 5th in there, and then 1 is going to fall on the floor. If you have bigger chunks of data or bigger chunks of items sitting on your desk, that means you can have fewer items to fit on that desk. And the constraint here is that you can't expand the desk. You can't increase that pipeline or increase the load or the load bearing object here. You just have to work with what you got, but you can compress the documents. And that's what give us a little foreshadowing to ways to hack this is maybe through compression, right? We can get around some of these, these 4 documents or these limiting 4 documents that we have. Let's talk about the bridge here between human and AI. The human, again, is the working memory, and we relate that or bridge that to the AI's context window. Again, the context window, for those of you that might not be familiar with it, the context window is that little window where you're typing your prompt into a large language model like a Chat GPT or Gemini or Claude. That's called the context window. You can think of it like the working memory for us. It's not the equivalent, but it's a good analogy for it so that we can, again, tie in the biology to the synthetic. Again, the capacity is 4 chunks for our working memory. Capacity for AI varies. The recent model by Claude that just came out last week, Opus 4.6, it has a fixed token limit of approximately 100, excuse me, not 100, but 1 million tokens. So that's a very large context window, which means a very large working memory set that AI model can handle, right? Ours is not nearly as large. The overflow info is overwritten or lost. And as it goes to AI, the overflow is the oldest tokens get truncated. So this is, again, why we have the issue of that long running context or long running memory with AI. If you're having a long conversation with AI, the oldest tokens, meaning the conversation or the information that you gave the AI at the very beginning of your conversation, as your conversation gets expanded, those earlier discussions, those earlier points start to get truncated or overwritten or lost, essentially. So again, that's where the AI starts to clip its memory and starts forgetting some of the earlier conversations and topics that were discussed in the prompt. As far as strategy goes, again, for working memory on the biological side, it's chunking to compress, right? If we only have 4 chunks, then we're going to try our best to compress information by chunks, by those 4 different chunks. And the strategy for AI to get around this limit is going to be summarization, RAG, or what's known as retrieval augmented generation, and pruning. So some pre-processing ways to clean up data, shrink data a little bit, reduce the size of data, reduce the dimensionality of data, and then using RAG, using some type of vector store or relevance or context extractor here. Now, the weakness on the biological side with the working memory, you get lost in the middle of lectures, right? Very long lectures, and I'm going to try my best to keep my lectures a little bit more concise as we go through this, because I don't want you guys getting lost in the middle of me talking to you. So the weakness with our working memory is that you get lost in the middle. You're hyped up, you're engaged. As we talked about with the RAS, you've got a little bit of excitement or arousal in the very beginning. But so as you get towards the middle, that sort of wanes off and you start to lose and drift a little bit. Same thing happens with our working memory limits. Now, the weakness with the AI side is that there's a loss in the middle of long context. Again, it's not necessarily just lost in the middle. I believe it's also lost in the beginning too, because those tokens get truncated the older they are. So those are 2 weaknesses. Again, the longer the material, the longer the session that you're either you as a human or as your AI that you're developing, the longer that session may be, the opportunity for data loss or information loss. Now, the axiom for this is an LLM or large language model's context window is its working memory. Both systems face the same core constraint, which is a fixed processing capacity that forces strategic compression of input. So key word here is going to be compression. You're going to see that a few times. That's essentially the way we're going to get around a lot of this. Now, let's talk about the breach protocol. How can we hack this limiting 4 chunks that we got? Well, there's a few ways we can do it. Number one is going to be to group by patterns, right? So if we can group the information by patterns, cluster related items into categories, this helps. This helps us retain information. Think about it. You got 9 random grocery items, but they can become 3 chunks if you break them down into related groups or categories like dairy, produce, and grains. Right. So now your brain can think about it in categories as opposed to individual items, which again free up some of the bandwidth that you have. Number 2, you can build hierarchies. So being able to nest details under parent concepts, right? So again, this is a way of stacking and seeing how things flow downstream or even upstream, right? Having an entire framework becomes one chunk with sub items you can unpack later. So again, this is similar to categorizing. Instead of using patterns, we're using hierarchy here. But what we're doing is essentially saying, okay, I have a folder, and then within that folder, I have a subfolder or a subdirectory. And you know that, okay, if I have a folder of images, but within those images, I have images of vacation, then I have images of family, and then I have images of, maybe something that I'm working on as far as a personal project. But you know that there's a hierarchy of that structure. And because of that hierarchy and using that framework, you're able to quickly manage the information that you're working with. Number 3 is going to be encoding with mnemonics, right? So again, the compression ability here is major, being able to compress a list into a single acronym or phrase. So Roy G Biv, right? So one chunk instead of 7 separate colors, right? So these are just, again, this is just the color spectrum here, but you can chunk that. That's just one chunk. But what you did was you created an acronym for it. So using an acronym is another way that we can register information or recall hooks that recall information for us. And then finally, another way to breach this protocol or another strategy that we can use is the process then clear. So again, you're thinking about mastering one chunk before loading the next. Like a piano student, learn measure one, then you learn measure two, and then you combine. So just thinking about it, kind of eat what's on your plate before you go back to the buffet and get some more. And this is just a way, if you think about it in the way that we're going to be constructing AI, is that you really want to think about it in a procedural, stepwise process where you're taking each item or taking each workflow, breaking them down into steps. You're doing the same thing here, except it's with information. You want to process the information so retain the things that you understand before trying to understand everything. Now, there are some caveats here. Obviously, if you're trying to get the big picture of a particular topic that you're trying to learn, maybe you do benefit more from seeing the big picture first and then breaking it down into little small submeasures. But that's entirely, depending on the particular topic that you're learning at that time and the individual as well. All right. So that's our breach protocol. What about the build? So what are we building this week or this for this class? What are we going to be building? So the first thing we're going to do is, again, create a chunking protocol, right? Using one of those 4 strategies or maybe all 4 of those strategies. But the goal is to create a repeatable system for breaking complex documentation into working memory safe units. So, right, you have this large document. Maybe it's a research paper you're trying to read. Maybe it's a script that you're trying to learn for. Maybe you're trying to prepare for a meeting, or maybe you're preparing for something that maybe you're an actress or an actor or something like that. But you have this large document, this large database or data source of information that you need to essentially ingest, and you may not have a lot of time to do it, right? So just imagine trying to read a novel in, a 400-page novel in a weekend. Right? Now, some people can do that if they have the training and they have the experience of doing that. But for most people, they're going to need, cliff notes, essentially, right? They're going to need to break down the complex documentation, which in this example is the novel. They're going to need to break that down into working memory safe units. So for my architects, my non-technical people, the way you're going to use this chunking protocol is you're going to design a manual chunking protocol template that any learner can use to decompose complex topics into 4 chunk sessions. Right? My builders, you're going to be building a chunking protocol system prompt that will instruct an AI to automatically decompose any documentation into a working memory safe unit. So think of it as essentially creating some type of summarization or chunking or breakdown of a very large document with your prompt using AI to help you do that for my developers. Let's go a little bit deeper into the requirements for each of our identities here that we have. My architects, what you guys are going to be working on, the first step that you need to do in your protocol, you need to make sure you're scanning. So make sure you identify all concepts in the source material. So, you don't want to leave anything out because you don't want certain information to be front loaded in the 4 chunks. Maybe you have 4 chunks you're breaking things down into. You put all the information in maybe 1 or 2 chunks, but then you forget that you didn't maybe include a source or a concept from the source. Right? So make sure you're including all the source or all the at least key concepts in that source material. And finally, then you're going to group. All right, we're going to cluster related concepts, max 4 per group. Then you're going to label. Right. So you want to label, name each chunk with a memorable header, and sequence, order chunks from foundational to advanced. So again, kind of building a story, so to speak, with your material. And then finally, verify, confirm each of your chunks stands alone as a learnable unit. Because again, what are you doing? You're learning each chunk individually, and you're going to stack those together. So make sure each one of those each one of those units, so chunkable units, are learnable. Now, for my builders, your system prompt must include to the AI, must instruct the AI to accept any complex document or topic as input. You may also want to put some constraints on here on the type, the file types. Is it going to be a PDF? Is it going to be a markdown file or MD file? Is it going to be a text file? Is it going to be a website or HTML? Make sure you include some constraints there as well. Decompose it into 4 top level chunks. Again, keeping the concepts, make sure you gather all the concepts. You want to label it as well, label your data. We want to label our chunks just as well. Label each chunk with clear descriptive headers. Then you're going to limit the sub items to 4 per chunk, right? So this is a way for us to nest those related information together, creating a little bit again of a hierarchy framework. Then you'll output a sequence learning path with dependencies, and finally include retrieval questions per chunk. It's similar like as we did from lesson 2. So maybe if you want to, in your retrieval questions, pose some questions or some topics that were covered in lesson 2 and see if you can get your AI to develop a script that will work for any one of those chunks. Now, the stack here is going to be combining this with your lesson 2 high salient system prompt for maximum effect, chunked in salience optimized output. So we're going to take our previous activity that we did and we're combining it with this class's activity to give us, again, a super optimized output from our AI. All right. So pretty good activities for both the builder and the architect. Let's run through the key takeaways from today's class. Number 1 is going to be the working memory, right? You can only hold 4 chunks of information in your brain. So remember that when you're trying to learn something or when you're sitting down to learn some information, remember you only got 4 space holders essentially that you can fill information with. Number 2, Miller's 7 was a rough estimate. Cowan's 4 is the verified limit. So we initially thought back in the 1950s, that 7 chunks was what we could handle inside of our brains. But that's been updated as of 2001 by Cowan. And then number 3 takeaway is a large language model context window is its working memory, and it faces the same bottleneck as our working memory in our biological systems or brains, all right? Number 4 takeaway is chunking is the universal hack, right? So you're going to chunk, and then you're going to compress the inputs to fit the fixed capacity. And then number 5 is stack your tools using, again, those activities and the builds that we built in the previous lesson. Lesson number 2, the Gatekeeper. We're going to bring in the high salience input in the chunking protocol from lesson 3, combine those together like Voltron and create this super optimized output result from our AI. All right, gang. Got it done pretty quickly. So again, not too long. Hopefully I didn't lose you in the middle and you were able to keep up with everything. If not, go back and watch the video, take some notes, do jot down what your assignments are for your builder and architect respectively. Next class, we will be talking about parallel processing, which is essentially dual coding and multimodal models. How do we process or ingest information, and process it using dual channels like our ears, our eyes, our mouths, our touch, our different senses? And how do AI models do that, what we call multimodalities or multimodal, when they're taking in audio files, image files, video files, text files, and now even up to physics or real world engines. So we'll talk about that next class. But until then, thank you so much for your time. Thank you for allowing me to serve you. Class is dismissed, and enjoy the rest of your week. Peace.